So welcome to talk about something which is a bit futuristic, not really available in production, but let's see what we can do in the near future, perhaps. So I'm going to talk about Idris, but through the angle of what does it enable us to do, how expressive can we be with the domain, and can it bring domain-driven design a little step further. So why am I doing this talk, or why am I exploring this kind of thing? Well, of course, because it's really cool. First time I saw it, it was just blew my mind. That's good enough a reason for doing it, of course. But more importantly, when something is really cool and awesome, sometimes when you dig deeper, you see that it actually has some real usages. It actually has some value in it, which can be applied in some context. So the possible value that we might get out of dependent type would probably be around making impossible states impossible. Like, there are things that are not legal input. There are things that our functions have to handle but have no sense for the user. If we can make those things impossible, then the code is simplified and we don't have to bother with these things. That would be really cool. There's a very, very good talk that I recommend from an Unconference with exactly that title, Make Impossible States Impossible. And it shows how we can do that without dependent types, and we can actually do a lot of things with fairly ordinary languages. Possibly it could also give some guarantees. You know, like there's a saying which I don't really encourage, is that it compiles so it's obviously correct, right? maybe, you know, in this kind of powerful language, maybe that can be true. Who knows? But possibly it might give some guarantees. So let's look at what we can see here. So first of all, in type-driven development in general, there's this idea of type, define, and refine. And it kind of changes a lot of how we code. And it has some interesting parallels to test-driven design. So let's have a look at how that works through a demo. So I'm going to ask you some help, because I'm going to switch between like a mirrored screen and not mirrored screen. So if ever I forget to mirror my screen when I go into a lab demo, please just tell me, you know, that we don't see any code. So let's say that is this a resolution? No, it's not a good resolution, right?
Oh, increase it.
Right. So this is better.
Yep.
So let's say that we want to write a function that concatenates to, or zips to two lists. So we could write zip, and that would take a list of something and another list, and it would return a list of A and B. So this is kind of ordinary. This is like generic types, or this is something we can do in many languages. And because it's so constrained, the number of possible solutions is not that big. And we can, in Idris, we can, once we've defined the type of thing, we can push the magic button, and it will generate a skeleton of code for us. And so here, what we see is we have zip for XS and YS, are two lists. And here we have an implementation in form of a whole. So I can ask the compiler, what is the type of this whole?
Johan, can you increase the font?
Oh yeah, I was going to ask the same.
The font?
Yes.
Yes.
Size.
I don't know. We fixed this would probably be better. We fixed that earlier. No. Kind of calibrated that just before. No, and okay, that's good.
Yeah.
So yeah, it's pretty much what we have before. So what is the type of this hole here? And will show us that this hole has the type list of A, B, of course. You know, that's the return value. But it also tells us what kind of variables do we have available to do that. And this is not going to be enough, so we have to do something more. We have to case split to solve this problem. So I'm going to push the magic button again, and I case split. So we have the empty array or a non-empty array, you know, in the second line here. And and I'm going to have to case split more here. So that here we have the empty array and the empty array, and so on. So now that we have this thing here, we can basically ask it to solve the problem for us. So how does this work? Idris said that, okay, I need to return a list of A and B. What is the simplest thing that will type check? And it will put that in place. It can be quite helpful sometimes, you know. On the other hand, sometimes it does not work out so well. So there's another interesting case, which is this last case here. So for all these, it will obviously be the empty list, right? But here, we probably need to do like X and Y, and then concatenate that with a recursive call to zip of XS and YS. And that, now actually what I wanted to do in this thing here was to, let's put back a hole here and ask the compiler to generate the solution, which is incorrect, of course. And sometimes when Idris doesn't help us in this way, it's because our types are not precise enough. They're not telling the whole story. We haven't extended the domain. So what we can do is we can write a zip of vectors. Vectors are a type which are more interesting because they have a size. So I have a vector of size n of a's, so a can be string or int or whatever. And then we have a vector of another length of b's, and that returns a vector of some other length of a and b. So this is basically the constraint that we had in the list solution. There is no links between the n, the m, and the l. And we can enforce that link by saying, okay, so this is an n, and this is an n. And it's only possible to call this function if we have those same size arrays. So if we ask Idris to generate the solution for us, then we do case split here. And if we look at the type here, it's interesting because Idris knows that ys here is of type vector 0 of b, is the empty vector. So now, when we case split, there are no other cases. There are no two cases for ys. And obviously, of course, this is vector 0 so the only solution for this is the empty list. And likewise here, if we look at the type here, we know that ys is of length superior to, so this is s plus 1, len plus 1. So it knows that ys is one longer than xs, which means that when I case plate here, there's only one possible case. It's y and then another ys. And now that we look at this, the type here, we can see that we have everything we need to solve the problem. We have a vector of length a, a vector of length b, of which it can do a vector of a and b's, but not of the right length. But luckily, it has x and a y first. So if we ask it to solve the problem, that's the simplest solution that passes the type checker. So now we know that in this case, we have very good types. Right. So
Can you say more about why it wasn't able to do this with the list?
with the list,
Yeah. Why was the size relevant?
because the empty vector is a simpler solution than,
So it's able to find it.
yeah. So it found a simpler solution, so it chose that one.
Yeah.
So it brings a lot of guarantees, but let's look at another guarantee that we can offer. Let's say that we forget to implement some cases. And we ask the compiler if everything is okay. The compiler said that everything is okay. That's kind of pity, right? So we can do something called enforced totality. So this is a flag to the compiler, which says that it'll have to check for totality. Totality means that for every input, it has a return value. And that's another very good, nice guarantee about a function. We don't have to handle the fact that it blows up in runtime, you know. So this is what we usually do. And whenever we need to define that a function is not total, then we say that it's partial. This can be the case for modulo, for instance, modulo which is not defined for integer division, which is not defined for 0. And now it passes the type checker. Right. So we've seen that we start by typing things, and then a little bit later we kind of refine those types because we realize that there are impossible solutions. There are illegal values in it. We have to handle illegal values. So as we develop the solution, we learn more about the problem and we introduce more precise types, either by using existing types or by creating them ourselves. So this is the type define refine cycle. We use dependent types. So the fact that the return value depends on the type of the input value. And here we can see that a vector of length 3 is not the same type as a vector of length 4. So we have parameterized types in our languages, but we don't have this kind of like numerical types that are different, which brings a lot of power. We develop with holes, so we can do a partial solution, then we can ask the compiler to help us. And because of that, we have a very nice compiler. It's not at all the kind of thing that like punishes you with a marginally understandable error message. It kind of helps you to solve the problem. And it kind of has a proof search. Proof search is provide the simplest possible solution that solves the problem. It's called a proof because a value is a proof that I was able to construct that. So it searches for a value that solves the equation. So that's a value is a proof, therefore it's a proof search. Right, so, and we saw about totality. What about unit tests in this thing? Do we need unit tests? Do we need unit tests? Well, no, of course, compile, so we're good, right? No, that's definitely not true, because while it was true in this case, in the general case, it's not true. If we look at something, sorry? Yes, it's not responding. Sorry. Well, maybe if I go to the end of the presentation, then everything will be, no. Fix the bug. So let's look at something different. So if we do fizzbuzz, then it's not because we have like an input NAT here and then we return a string, and if it's divisible by 3 and by 5, then it's fizzbuzz. The type system is not providing us that kind of guarantee now. So we need unit tests. So we write those unit tests, like normal Haskell kind of way of doing things. So for all 1, 2, 3, 4, well, it should be like just a number, right? But we can be more strict about our types. So instead of having this solution, we can spend a lot more time coding and create a lot more code and have a stricter solution. So what we have here is we've introduced a fizzbuzz type, and it has 4 constructors: fizz, fizzbuzz, and normal. In order to construct those things, I have to provide the number and a proof that that number is a fizz that is divisible by 3. And that is not divisible by 5, because otherwise it would be a fizzbuzz, right? And so on and so forth. So with this, I know that given a number, I will always create the right type. But what the compiler cannot ensure is that do we translate the right type to this kind of number? And for instance, in particular, this one is the one that still needs unit tests. So types can remove some errors, but they can't remove all of them, or some of them they can't. In particular is when we want to do some output. At that time, we're loosening the type constraints, so we'll always need tests at that place. Interestingly, in this kind of language, you can write tests in a different way. We can have the compiler run our tests. So this is an example of this. So I have a test, 3 is fizz. So it is it's a value that says that show fizzbuzz for 3 equals fizz. And this is like an equality type. So this is verified by the compiler. And the compiler says that REFL means obviously true. The compiler actually calls the show fizzbuzz for the 3 and replaces that with the result of that, which is fizz. So if we look at the type here, we can see that, well, no, we don't see that. But anyway, so if that would be wrong, the compiler would change that. So if I have the wrong test, then it says that 4 is not equal to fizz. So this is, I don't know how useful this is, but it's certainly very funny. And and we can extend this to like, okay, I can do more or less parameterized tests. So I have like a pattern matching of any integer, and for when the integer is 3, 6, 9, 12, etc., then it is fizz. So oh yeah, I should close this one right now. So for this n, it is fizz. And this is a partial function, so it's not true for all inputs, right? So the compiler runs our tests, meaning that we'll have to revise our statement if it compiles it's obviously correct. Anyway, I find that very funny. And I find it an interesting way of writing tests. So we can bring those a bit further. So we can make those like more or less property-based tests, but it's sometimes that's a bit tricky. In this particular situation, it was too tricky to do that, so I stayed with example-based tests. But I think it's just a matter of my level of understanding of Idris yet. Let's look at another important thing, which is small types. So this solution here, it's nice because it's very strongly typed, but it does not scale. If we introduce bang, so in FizzBuzz, you can say that, okay, for every 7, I say bang. And then you have a problem because you have fizz bang, buzz bang, fizz buzz bang, and you have bang and all kind of combinations. So I had 4 constructors here. I will end up with 8 of them. So it does not scale. And also, not only will I have more lines, but I will also have more arguments to the constructor because I have to prove that it is a bang or not a bang. So it's not extensible. Some people say that this is due to statically typed languages. They are not extensible, but that's only partially true. If we take another approach and we say that FizzBuzz is not a type in itself, it's composed by 2 other types. The fizz type, which is either fizz or not fizz, and the buzz type, which is buzz or not buzz. And the fizz-buzz type is just the tuple. So the pair of a fizz type and a buzz type, then I can represent all the states for that. And it naturally scales because if I want to do fizz, buzz, bang, then I will not use a tuple but a 3-tuple. And also I can still keep the functions that work on only fizz, buzz and introduce a new function that works on fizz, buzz, bang. So it's composable. So in these languages, while our types are closed, we cannot extend existing types. We can compose with types. So it becomes important to keep the type small. And by keeping the type small, I mean few constructors, few lines, and if possible, few arguments. I have a feeling that kind of maps to the OO world, where we sometimes say that, okay, composition is better than inheritance. Well, we should favor composition over inheritance in many cases. Not all, but in many cases, because that's more composable. Sometimes when you want to extend like a big mother class will have loads of methods, you're just annoyed because it has loads of methods you don't want, and you throw exceptions, or you do fake implementations of them and stuff like that. Same thing here. You're annoyed by the data in the type that you are extending. Right, so these are all very fancy types, but at the end of the day, everything the user inputs is string. So how can these things be useful? Well, if we validate the user input, then we can construct very refined types. If we know a lot about the input and we just return, do error messages or solve the problem, or make the data valid, like Michael talked this morning, then we can have strong types. But the corollary is that we have, in our domain, the core of a domain, we define our functions with very specific types, then we are enforced to do validation, because otherwise we cannot call the function. So we're enforcing pre-constraints. An example of this is, in that way, once we can call the function, it's a proof that we have the right to do so. Types is very much like a proof that we are in a valid situation. And this is true in like normal languages, because if we put assertions in the constructor or in the builder that creates those objects, then the whole application can believe in our right to do things and have less validation to do. In a language like this, this brings very interesting things. So in Tic Tac Toe, if I want to place my marker at a position, I have one option up there. Like I have 3 positions, and I put my position, and I get a list of positions back. That doesn't tell us a lot about the nature of Tic Tac Toe compared to the one below. Here we have 3 positions which are at least 1, n plus 1. And we have a position, and we know that the position is an element of the 3 positions. This is a proof that states that this is valid for P and 3 pos. And then it returns a vector of less. So this means that we're going to end the game at the latest whenever we've played 9 times, because there are now only 9 positions. We call this 9 times, then there is no way of calling this anymore, because we cannot provide this kind of argument with suc_n. And we cannot call it with a position that is already taken by some player, because we need to provide the proof that it's in the prepositions. And the position is a valid position. It's not something which is outside the board. I haven't shown you how I did that, but it's basically done with an enum. So what will happen is we kind of put the responsibility onto the user, validate the input before you call this, but then you get very nice guarantees about and you get types that describe the problem in a more precise way than what normal language can allow us to do. Is this very useful? Does this remove bugs? I don't know yet. But it's certainly very nice to have this kind of fine-grained tool and be able to encode knowledge. Like coding is encoding knowledge. And I can encode more knowledge about the problem domain with this type of features. So in that way, it's a bit like test-driven development, because as we code, we learn more about the thing and we constrain things more. Have an iterative cycle. It goes back to type definer vine as well. An interesting question is, do we have fast feedback? So say that in non-typed languages we have fast feedback. Yes, we do, because we have no compilation, and we can sometimes hack our way away and get some quick feedback, because the whole application does not have to compile, just the thing we're testing right now. And that's true, but there's another type of feedback that we don't have fast in non-typed languages, which is we don't have feedback about all our branches. At the very best, we run our tests to know about all branches, but then we have to have test also which covers all the branches. We also don't have feedback about type mistakes. I will talk more about that in the bug-free by design. But whenever I'm calling a non-existing method, for instance, or whenever I'm using the autocomplete, the feedback cycle is very fast in typed languages. So I'm not saying it's better, it's different. And I think that in non-typed languages, it has a great success, because we get faster to something that works in most cases, seems to be working, or works enough. And that's a real value, that you can say that, okay, that's shit because you can't be sure. Yeah, but no, it's not shit, because a lot of the time we just need it to work approximately. And at least that's very satisfactory. Okay, it works already, Right, so I'm going to skip this one because we don't have time, but we're talking about recursive types, how to model the domain with recursive types. And I'm going to talk about this one. So sometimes the types can be very clean. So this is a coin change kata, where we are having, say I have to give 95 cents of change, given that I can give a 10-cent coin, I can give a 50-cent coin, and so on. How can I compose that? What we can do here, we can define a function that for any amount returns a change of amount. And it's impossible to implement anything that returns 93 when number is 95 in the beginning. It's really cool. In this case, we don't have to test that, right? And what we do is we define a type here. We have like 140, no change, so that's no coin, right? And whenever we have one coin, and then we have like the remaining amount to give change for. And then we give like a proof that value plus previous amount equals the amount. And that means that we have a type of change amount. So this is easy to type. It's excruciatingly difficult to implement, and the code is unreadable. So that might be partially because I'm not so skilled in Idris. No, maybe when I'm more skilled, I will be able to do a simpler solution. But I doubt that it will shrink too much. So this would be very easy to implement in normal code, and it would be like a very understandable solution. So in this case, it's like a big trade-off in between. I have guarantees in the type, and I spend more money implementing that, or even maintaining it. Maybe that can be like a good trade-off in some cases. Maybe not, because if it's not so readable, is it maintainable? All right, so I'm going to finish on some conclusions of this exploring. So types are proofs, and that's something we can use in real life. If we have a phone number instead of a string which represents a phone number, then it's a proof that it's valid, if there are assertions in the constructor. Compilers can work a bit like tests. You can even implement tests in the compiler. When we do type-driven development, we should aim for small types. And when we have qualified types, that means we have encoded knowledge. I think that's probably the most promising conclusion that I have done through these experiments, is that it allows me to encode more things. So there's a thing about the feedback. Feedback in dynamic and static type languages is a bit different. And I have the impression that the compilers will evolve and bring us more of the things that we see here, like interactive type information and using very refined types to give very qualified information, and even running our tests, perhaps. Right. Do you have any questions? Yes?
Well, yeah, a bit of a question, I guess a bit of a comment. It's funny with the case of zip that we need to basically specify size so we're going to get the full inferencing to be able to produce an implementation, right? And what I kind of wonder about with this is that whether some of this tooling can actually be a little bit more liberal with the suggestions to go and say, it seems like a very easy thing to be able to go and say, well, this might be what you want, as opposed to this is the only thing it can be.
Yeah.
And I kind of wonder about this too, because it's kind of like with JavaScript and the move to TypeScript. I think that was held back for many years because we had this thing that everything had to be sound, type soundness. And when instead we could actually go and basically make some reasonable suggestions based on what we see already. So I wonder if this is another one of those areas where the tools are overly conservative. They could be a little bit more loose about things and let people select possible implementations based on what they've seen so far. If you have any thoughts about that.
Well, it could definitely propose like all possible solutions,
Yeah, but
and I will choose one. Sorry?
I mean, like for instance, the zip on lists. It seems like it should be able to see that would be probably the easiest thing it could suggest others.
Yes, yes, and I could suggest many possible things, and I will just select one. That would be really nice, and that would definitely be possible. And it wouldn't at all break the nature of this.
Although it seems like with this, it seems like it's trying to go and basically only give you the things that they can demonstrate really are true. So there's a proof aspect to it.
No, but it can demonstrate that the solution to the vector would be true also for the other one.
Well,
so it is in the space of possible solutions.
Yeah.
So
So I guess you generalize the type afterwards, a possibility, right? We can move from array to vector because we can see. We move from vector to list because we can see that's a possibility.
Well, it couldn't return a vector, but it could return, like, there are many ways of creating a list with the right type.
Yeah.
So it could have like 1, 0, or n or whatever amount of elements in it. So there are many possible. There are more possible. The solution space is bigger in the list case, and it includes the solution that I used for the vector.
Yeah.
So it could definitely do that, and that would be a nice feature.
Yeah, I agree.
Yeah.
How is the interoperability with other languages? Can you produce some static libraries, shared libraries?
No, no. I think that's a really, really big problem because there's no interoperability with Haskell. It has to do with the totality of the language and its possibility of verifying. So you cannot. There's a thing with polymorphic data types. So if you introduce languages that have another approach to polymorphic data types, then you cannot prove totality anymore. So in that case, you might have to do something like TypeScript does, like, okay, so we leave some of the proofiness of the language in order to do that. I don't think they have another solution for that quite yet.
And if the compiler detects that it's not totally typed correctly, if you write a function, will it generate tests for the partial cases?
Sorry, can you repeat the question?
You have a bigger domain that
Yeah.
you need to treat like 10 use cases, and in your function you only write 2 cases for an empty list and for size 1. It will generate unit tests for the partial cases, or you need to define the whole domain?
The Idris compiler does not generate the tests. I write the tests, and the compiler runs them. Does that answer your question, or?
So the compiler, you write the test.
I write the tests, and I use the compiler to execute them. Other questions? So if you're interested in this, please come and see me. I have lots more of code to show and lots of katas that I've done, and I'd be happy to talk about that.
Thank you.
Right. Just one last comment. I'm doing a talk about bug-free also, and disclaimer is I don't think that bug-free software is only about static typing. Far from it. This is just an exploration of going to the extremes of some tool to see how far can we go. All right. Thanks.